Welcome back to the session on Fourier transforms. In this session, we shall discuss the main property of Fourier transform, which is known as the Parseval'S modulus theorem for Fourier transforms. The theorem is, if the Fourier transform of a function f of t is equal to f of omega, then we can write integral from minus infinity to infinity modulus of f of t the whole square dt is equal to 1 by 2 pi into integral from minus infinity to infinity modulus of f of omega the whole square d omega. This is the Parseval'S theorem for Fourier transforms. In order to prove this theorem, we have to know the Fourier transform. The definition of Fourier transform is Fourier transform of f of t, which is a function of f of omega. It is defined as integral from minus infinity to infinity f of t into e raised to minus I omega t dt. The convolution between two functions f of t and g of t, it is denoted as f of t star g of t, which is defined as integral from minus infinity to infinity f of lambda into g of t minus lambda d lambda. This is the bilateral convolution between the two functions f of t and g of t. If it is unilateral, then the limits of the lower limit of this integral will become 0. That is f of t star g of t equal to integral from 0 to infinity f of lambda into g of t minus lambda d lambda is known as the unilateral convolution. Now, consider here f of omega as, by the definition, it is integral from minus infinity to infinity f of t into e raised to minus I omega t dt. This is the definition of Fourier transform. Now, we are replacing the variable omega by minus omega. We can write this as f of minus omega is equal to integral from minus infinity to infinity f of t into e raised to minus I of minus omega t, that is e raised to I omega t dt. Now, we are taking the conjugate on both sides. We get f of minus omega conjugate is equal to integral from minus infinity to infinity f of t conjugate into here e raised to minus I omega t dt. This is the definition of, we can write this as the Fourier transform of, here the function is f of t conjugate. That is, f of minus omega conjugate is the Fourier transform of f of t conjugate. Now, we know if the Fourier transform of f of t is equal to f of omega and Fourier transform of g of t equal to g of omega, then the Fourier transform of f of t into g of t, that is the product Fourier transform of product of f of t and g of t, is given by 1 by 2 pi into f of omega convolution g of omega. This is the frequency convolution property of Fourier transforms. Here this is the Fourier transform of f of t. That is, Fourier transform of f of t is equal to f of omega, and Fourier transform of f of t conjugate is equal to f of minus omega conjugate. Then we can write the Fourier transform of f of t into f of t conjugate as 1 by 2 pi into, this is the property, Fourier transform of a product is 1 by 2 pi into corresponding Fourier transforms. Therefore, we can write here 1 by 2 pi into f of omega convolution. The Fourier transform of f of t conjugate is f of minus omega conjugate. Now, expressing both sides as integrals, we can write in the left hand side as integral from minus infinity to infinity f of t into f of t conjugate into e raised to minus I omega t dt. That is the definition of Fourier transform, which is equal to, the right hand side is 1 by 2 pi into, here this is the convolution between f of omega and f of minus omega conjugate. By definition of convolution, we can write this as integral from minus infinity to infinity. Here we can write f of omega, convolution between f of omega and f of minus omega. That is, we can write this as f of some tau into, here we can write f of minus of some omega minus tau, the conjugate d tau. This is from the definition of this convolution, f of omega convolution f of minus omega conjugate is integral from minus infinity to infinity f of tau into f of negative of omega minus tau conjugate d tau. In this expression, put omega equal to 0, which gives integral from minus infinity to infinity f of t into f of t conjugate. Here e raised to 0 is 1. Therefore, this into dt is equal to 1 by 2 pi into integral from minus infinity to infinity f of tau into, here omega equal to 0 means this is negative of 0 minus tau, that is negative of negative tau, that is tau, f of tau conjugate d tau. That is, this gives integral from minus infinity to infinity f of t into f of t conjugate is, we can write modulus of f of t square into dt, which is equal to 1 by 2 pi into, from here we can write integral from minus infinity to infinity. This is f of tau into f of tau conjugate means modulus of f of tau square d tau. This is the Parseval'S modulus theorem, or this equation is known as Parseval'S identity for Fourier transform. Now, we have to work out some example problems. First one is verify Parseval'S theorem for the function u of t into e raised to minus t. This is the given function. We have to verify this identity for this function. First of all, we denote the given function by f of t, that is f of t equal to u of t into e raised to minus t which is defined as e raised to minus t for t greater than 0 and 0 for t less than 0, because the unit step function is defined as u of t is equal to 1 for t greater than 0 and it is 0 for t less than 0. Therefore, u of t multiplied by e raised to minus t is e raised to minus t for t greater than 0 and 0 for t less than 0. Therefore, we can write this left hand side of this identity as integral from minus infinity to infinity modulus of f of t square dt as integral from, here the limits of integration are in two ranges, that is the function is given by two ranges. T is greater than 0 means t is from 0 to infinity, and t is less than 0 means t is from minus infinity to 0. Therefore, we can write this integral as integral from 0 to infinity. In this case, the function is defined as e raised to minus t. Therefore, modulus of e raised to minus t the whole square means e raised to minus 2t. In this range, the modulus is the function itself, and the square is e raised to minus t whole square, that means e raised to minus 2t dt. On integration, we get e raised to minus 2t divided by minus 2 between the limits 0 and infinity, that is when t equal to infinity the numerator will tends to 0 minus when t equal to 0 the numerator is 1. Therefore, 0 minus 1 divided by minus 2 means 1 by 2. That is, the left hand side of this identity is 1 by 2 for the given function u of t into e raised to minus t. Now, we have to evaluate the right hand side also. Here f of omega equal to the Fourier transform of the given function u of t into e raised to minus t. That is, by the definition of Fourier transform, we get integral from minus infinity to infinity e raised to minus t into e raised to minus I omega t dt. Here e raised to minus t is for t greater than 0. Therefore, we can write this integral as from 0 to infinity. For minus infinity to 0, the function is defined as 0. Therefore, we can write this. This is equal to integral from 0 to infinity e raised to minus of t into 1 plus I omega dt. That is, on integration we get e raised to minus of 1 plus I omega t divided by minus of 1 plus I omega between the limits 0 and infinity. That is, when t tends to infinity, this term will tends to e raised to minus infinity, that is 0 minus, when t equal to 0, it is 1 divided by minus of 1 plus I omega, that is 1 by I omega plus 1 or 1 by 1 plus I omega. This is the Fourier transform of the given function, that is f of omega equal to 1 by 1 plus I omega. Now, modulus of f of omega square is equal to modulus of 1 by 1 plus I omega the whole square. By the property of modulus, we can write this as mod 1 divided by mod 1 is 1, modulus of 1 is 1 divided by modulus of 1 plus I omega. Modulus of 1 plus I omega the whole square. That is 1 by modulus of 1 plus I omega is root of 1 square plus omega square the whole square, that is 1 by 1 plus omega square. This is modulus of f of omega whole square. Now, integrating with respect to omega, we get integral from minus infinity to infinity modulus of f of omega square d omega is equal to integral from minus infinity to infinity 1 by 1 plus omega square d omega. That is equal to, here integral 1 by 1 plus omega square d omega is tan inverse omega between the limits minus infinity and plus infinity. On applying the limits, we get tan inverse infinity minus tan inverse minus infinity. That is, tan inverse infinity means pi by 2 minus tan inverse minus infinity means minus of pi by 2. Therefore, we get this equal to pi by 2 plus pi by 2 means 2 times pi by 2, that is pi. Therefore, we can write here the right hand side integral is integral from minus infinity to infinity modulus of f of omega square d omega is pi. Therefore, 1 by 2 pi into, this implies 1 by 2 pi into integral from minus infinity to infinity modulus of f of omega square d omega is equal to 1 by 2 pi into pi, that is 1 by 2, which is the right hand side. We got the left hand side integral as 1 by 2. Therefore, RHS equal to LHS. Hence, we verified the Parseval's identity for this given function. Now, consider the example, one more example. Find the Fourier transform of the given function f of t equal to 1 minus t square for mod t less than 1 and equal to 0 for mod t greater than 1. Hence, evaluate integral from 0 to infinity x into cos x minus sin x divided by x cube the whole square dx. We have to find the Fourier transform of this function and hence evaluate this integral. By definition of Fourier transform, we can write here Fourier transform of f of t as. Note that the given function is an even function. Therefore, the Fourier transform is 2 times 0 to infinity f of t into cos omega t dt. That is 2 times integral from 0 to infinity. We can split this integral 0 to infinity as 0 to 1 f of t into cos omega t dt plus integral from 1 to infinity f of t into cos omega t dt. This 2 is common. In this case, the function is defined as 0. Therefore, this is equal to 2 times integral from 0 to 1. In the interval 0 to 1, we can write the function as 1 minus t square into cos omega t dt. That is equal to 2 times, here we can use the integration by parts. First function into integral of the second is sin omega t divided by omega minus, here minus 2t, derivative of 1 minus t square is minus 2t into integral of sin omega t divided by omega is minus cos omega t divided by omega into omega plus derivative of minus 2t is minus 2 into integral of this is minus sin omega t divided by omega into omega into omega between the limits 0 and 1. That is equal to 2 into, when t equal to 1, this term will become 0. This is here there are 3 negatives, therefore this is minus t is 1, cos omega into 1 means cos omega divided by omega square. Here there are 2 negatives, therefore this is plus 2 into sin omega divided by omega cube minus, when we apply the lower limit 0, here sin omega into 0 will become 0, this also 0, this third term also become 0. Therefore, Fourier transform of the given function is 2 times minus cos omega divided by omega square plus 2 into sin omega divided by omega cube. We can write this as 2 into omega, here 2 sin omega minus omega cos omega. Here there is minus 2, therefore we can write from here this is 2. Therefore we can write this as 2 sin omega minus 2 omega cos omega divided by omega cube, that is 4 into, if we take this 2 outside, we can write 4 into sin omega minus omega cos omega divided by omega cube. This is the required Fourier transform of the given function. Now we have to evaluate this integral. For this we take f of omega as this function, that is f of omega equal to 4 into sin omega minus omega into cos omega divided by omega cube. Then we have to use this Parseval'S identity in order to evaluate this integral. Now consider this integral, let it be I, that is I equal to integral from 0 to infinity x into cos x minus sin x divided by x cube dx. Here we can write this as here this is here whole square. Therefore, this integrand is even. Therefore, we can write this as 1 by 2 into integral from minus infinity to infinity x into cos x minus sin x divided by x cube the whole square dx. By the property of definite integral, we can write this integral from 0 to infinity as 1 by 2 times integral from minus infinity to infinity, because this integrand is an even function. Now we change the dummy variable x into omega. We can write this as 1 by 2 into integral from minus infinity to infinity omega into cos omega minus sin omega divided by omega cube the whole square d omega, by changing the variable x into omega. this is equal to 1 by 2 into, from here we can write, we denote f of omega as 4 times sin omega minus omega cos omega divided by omega cube. Therefore, we can write here integral from minus infinity to infinity, this also, that is omega cos omega minus sin omega divided by omega cube is from here 1 by 4 f of omega. Therefore, here the whole square means we can write 1 by 16 f of omega square d omega. Now, we use this Parseval's identity. From this identity, we can write this as this is equal to 1 by 2 into 1 by 16 means 1 by 32, integral from minus infinity to infinity modulus of f of omega whole square d omega is. By using this Parseval's identity, we can write this integral as 2 pi into, that is this into 2 pi into integral from minus infinity to infinity modulus of f of t whole square dt. Here f of t is defined as 1 minus t square the whole square dt, which is equal to 2 pi divided by 32 into, this is this integrand is an even function. Therefore, we can write 2 times 0 to infinity 1 minus t square the whole square dt. That is equal to, here 2 by 32 means 1 by 16, then 2 by 16 means 1 by 8, that is pi by 8 into integral from zero to infinity. Here the function is defined as like this, for mod t less than 1 means between minus 1 and 1 function is defined as 1 minus t square. Therefore, we can take the upper limit as 1, 0 to 1. In all other cases, the function is defined as 0. Therefore, we have to take here 0 to 1 here also. Therefore, we can write this equal to pi by 8 into integral from 0 to 1 minus t square the whole square dt means 1 minus 2 t square plus t raised to 4 dt. That is pi by 8 into integral on is t minus 2 into t cube by 3 plus t raised to 5 divided by 5 between the limits 0 and 1. When t equal to 1, we get this equal to pi by 8 into 1 minus 2 by 3 plus 1 by 5. When t equal to 0, all these terms will become 0. Therefore, this is equal to pi by 8 into, from here we can write the LCM is 15. Therefore, 15 minus 10 plus 3, that is 15 minus 10 is 5, 5 plus 3 is 8, and this 8 and 8 will be cancelled. Therefore, pi by 15. This is the value of the required integral, that is integral from 0 to infinity x into cos x minus sin x all divided by x cube the whole square dx is pi by 15. We evaluated this integral using the Fourier transform and this Parseval's identity for Fourier transforms. With this example, let me conclude this session. Thank you for listening this session. Have a nice day.